Hello students, in view of request from students, I am preparing a video related to Grignard's reagent. What is Grignard's reagent? Preparation and its behavior towards different functional groups in chemical reactions. These are the things we are going to see in this video. See, Grignard's reagent, it is nothing but RMGX, general word, alkyl magnesium halide, or sometimes this may be replaced by an aryl magnesium halide. This is said to be Grignard's reagent. See the general method of preparation. An alkyl halide with magnesium metal in dry ether. See, magnesium has 2 electrons in its valence shell. Here nucleophile can attack on this. See, it gives 2 electrons to this carbon part and this bond pair push on to halogen. Now what I get? See, for this carbon, see this pair, say out of this pair, one belongs to this carbon and another one to this halogen. Now if this pair moves towards this, loss for this carbon is 1 electron, but here it is gaining 2 electrons. So net change is increase of 1 electron, addition of 1 electron for this. So because of that it becomes R minus. Whereas magnesium, loss of, say for magnesium there is a loss of 2 electrons. So it is plus 2 and this is X minus. So R minus Mg plus 2 X minus. This is written as RMgX, alkyl magnesium halide. Okay, this is the general method of preparation of Grignard's reagent from alkyl halide. Here, now the question is, why do you use dry ether as the solvent? Why not water or ammonia or alcohol? See, to explain that, let's see the, for that purpose, let's see the reactivity of Grignard's reagent. See, if you look at the structure of Grignard's reagent, the charge on alkyl group is minus, on halide is, halogen is also minus, on magnesium plus 2. See, here both R minus and X minus both can act as nucleophile. But between these two, which is better nucleophile? C minus, because which can donate electron pair easily? C minus. This is less electronegative, whereas this is more electronegative. So because of that, its tendency to give up electrons decreases. Okay, that's why here we concentrate on alkyl part. See, alkyl R minus is the good nucleophile here. R minus, hereafter I would like to use this way. I would like to follow this way, R minus Mgx plus. Okay. Now if you look at this carbon part has negative charge. Because of that negative charge, this R minus can act as a base or as a nucleophile. There are 2 possible ways for R minus. Okay, again base means, see, it may undergo acid base reactions or even it can carry out the elimination reactions depending upon the structure of substrate. Okay, as a nucleophile there are different possible reactions. Nucleophilic substitution may be possible, nucleophilic substitution or nucleophilic addition. There are different possible ways. Okay, so this R minus of Grignard's reagent can act as a base or as a nucleophile. Base means, see, it reacts with acidic groups or acidic substances. Okay, between these two, priority will be given to which one? Suppose if a reactant has both acidic group like this. For example, let's consider C double bond O and OH. Here our best example to understand this concept is, say, COOH. This is carboxylic acid. It can give up H plus, and here because of electronegativity difference, this carbon gets positive charge delta plus. So generally we expect donation of electron pair here and acid base reaction here. Here nucleophilic addition, here acid base reaction. Which is preferable? See, acid base reactions are fast. So if only one equivalent of Grignard's reagent is available, first it preferentially reacts with the acidic group. Okay, that's why. If excess of reagent is present, that reacts with both. That is a different case. Okay, like that. So priority will be given to this nature, if possible. Now let's see different reactions of or behavior of Grignard's reagent, towards different functional groups. For example, RMGX, see, with water, it can give up H plus, or with NH3, or primary amines like ammonia. Here ammonia like water self-ionization is possible, or secondary amine. Here still hydrogen is there, or carboxylic acids. All these compounds have acidic hydrogen, or even sulfonic acids, SO3H. See, because of acidic hydrogen, this R minus reacts with that H plus. See, these are acidic compounds. They can give up proton. So with that H plus, R minus with that H plus gives RH, alkane. So this is the behavior of Grignard's reagent towards acidic compounds. Okay, now let's see another group present in the given substrate. Suppose if the substrate has a carbonyl group, it may be aldehyde or ketone, maybe any C double bond. See, because of electronegativity difference, it gets delta plus, here delta minus. Here there is no acidic group. It donates electron pair to this carbon. If it reacts with H plus, then it is said to be acid, base. If it donates electron pair to an electron deficient center other than H plus, then it is called nucleophile. Now here it is acting as a nucleophile. See, we have seen in the topic in the previous video electrophiles, and please refer electrophiles and nucleophiles. In that video I have given clearly the difference between nucleophile and base. So here nucleophile, here it is acting as a nucleophile. See, it becomes O minus, this R is bonded to this. Well, after acidification, sometimes they may or may not give this H plus. After acidification, it becomes as an alcoholic group. See, if these valencies are satisfied by hydrogens, see, if they are satisfied by hydrogens, HH, RCH2, RCH2OH, then what do you get? 1 degree alcohol. If they are satisfied by one valency with hydrogen, another valency with an alkyl. The alkyl and H R2CHOH, that is 2 degree alcohol. If these valencies are both are satisfied by R and R, both are of alkyl, then we get 3 degree alcohol. In that way we get different products. Just to substitute the values. If both are hydrogens, primary alcohol. If one is hydrogen and another one is alkyl, RRCHOH, secondary alcohol. If both are alkyl, these both are already one alkyl is there, we get tertiary alcohol. In that way this behaves towards carbonyl group. Means here it is acting here nucleophilic addition, just nucleophile is added to this. Nucleophilic addition takes place. Okay. So this is the behavior of Grignard's reagent towards carbonyl group. And now see if other groups, for example acid chloride. Acid chloride are called acyl chloride. Here also this donates an electron pair to this, and these electrons are transferred onto oxygen. Then what happens? R dash C single bond O minus, here R, this is Cl. But the difference between previous reaction, carbonyl compounds, aldehydes and ketones, and this one is, here we have a good leaving group. So electrons delocalize like back this in this way, and loss of Cl minus takes place. Finally what you get? R dash C double bond O R plus Cl minus. Cl minus is not a good nucleophile. Previously we have seen in RMGX what I told you, which is good nucleophile, R minus or X minus? R minus. Okay. So here backward reaction is not possible in this case, right? If excess of Grignard's reagent is available, if excess of Grignard's reagent, if some more amount of Grignard's reagent is available, again your carbonyl group is there. Nucleophilic addition from this to this, from this starting this to this step, that is nucleophilic substitution. Cl minus, that is substituted by R minus up to this, that is nucleophilic substitution. Here this is just addition, there is nothing, there is no leaving group, that's why addition takes place. Now what do you get? R dash C single bond O minus, here R and this R. Okay, this is the product. After acidification, sometimes they may or may not give, that is you have to, they give the product directly. C R dash, and this becomes as OH, 3 degree alcohol, ketone plus RMGX, 3 degree alcohol is the final product. Okay. So here totally how many moles of Grignard's reagent is used? Here 1, here 1. If only 1 mole of reagent is available, reaction stops at this stage, right? So that is the behavior of RMGX. In the same way, with respect to esters, see what is ester? RCO R dash. Instead of Cl, if you have OR dash, in the same way, in place of Cl, leaving group is here, leaving group is O minus R dash. In the same way, you can work out with acid chlorides and esters. So this is the behavior of Grignard's reagent towards acidic groups, carbonyl groups, aldehydes and ketones, acid chlorides and esters. Okay, in that way we can see. And one more important point is, see this. Let's see this. You see this example, carbonyl group, RMGX. Here this is R minus, this is plus. Simply nucleophilic addition takes place here. Okay, what do you get? See here, single bond O minus, and this R is bonded to this. After acidification, that becomes as alcohol. But I look at this reaction, let's compare this to double bond O, here double bond. See the difference between these two? Here it has one double bond, and also this is in conjugation with C double bond. So what? Because of conjugation, see resonance structure, see electrons delocalize in this way. Here this becomes O minus, here double bond, and this carbon gets positive charge. Now tell me, see positive charge, see in this structure, positive, more quantity of positive charge is on 1 or 2, clearly on 2, because on this carbonyl carbon, due to resonance, see it gets delta plus, no doubt in it, because of electronegativity difference. But because of this delocalization, here this magnitude of this charge decreases. At the same time, here positive charges, more positive charges developed. So which is more reactive center towards a nucleophile? Clearly this one. So in this conjugated system, nucleophile attacks on that carbon. See, R minus MgX plus, see it donates electrons to this simultaneously. See conjugated carbonyl compound. Then what do you get? Here single bond O minus, here double bond, here single bond, and R is bonded to this. This on acidification, see the product, it is OH, here double bond, here R. See this is enol. OH is present on the double bonded carbon. Tautomerism is possible. Tautomerism, again these electrons in this way. Here this H plus is transferred from this to this carbon. What is the final product? See here it is double bond O. Here it is single bond. This is also single bond. Finally we have R. See this, check this. Nucleophilic addition is taking place in case of conjugated system. This is said to be this type of reaction in conjugated systems. Reaction of Grignard's reagent in this conjugated system is said to be Michael addition. This is called Michael addition. Okay. So what is the net reaction? This is the reactant. This is the product. See, compare this to the C double bond O remains as such finally. Of course, if excess of reagent is available, further it reacts. I am not talking about that. With 1 mole of RMGX, this is the product. If 1 more mole is available, that reacts with this ketone, finally gives alcohol, tertiary alcohol. So I am not going to discuss that further because we already done that type of problem. Okay, now compare these two. C double bond O remains as such. Only the difference is here this double bond is disappeared. To one part R minus is added, to the another part H from this. H from that. Okay, this is about Michael addition. So, but it happens in case of conjugated systems, right? If it is non-conjugated, then reaction is like this. If it is there is no conjugation, then reaction is common. Okay, next, and one more important point is, see this behavior of Grignard's reagent towards a carboxylic acid. It's a little bit different than expected. First step, see what I expect, generally a student expect R minus is there, C double bond O is there, so it attacks here. Why? Because of positive charge. At the same time, he is forgetting one thing. Here this hydrogen also has positive charge. This is released as H plus. Which has more positive charge, this hydrogen or this carbon? This one, because it is releasing as H plus. If there are two positive centers, now R minus prefers more positive center. Which is more positive center? H plus. I mean acidic. Acid base reaction first. Initially I told you, preferential, we have to give preference to acid base reaction. Okay, so nothing but this is the concept. Because of more positive charge, R minus readily combines with this H plus. So what do you get now? R dash COO minus plus this R minus with this H plus RH. Right. If excess of reagent is present, then what's the expectation from student? R minus MgX. Students generally expect because of C double bond O, it attacks here. But in case of Grignard's reagent, this is not possible. This attacking of Grignard's reagent on carboxylate ion is not possible. Why? That's the question. See the reason. See this. One thing is RCOO minus is resonance stabilized. Okay. RC single bond O minus, here double bond O. So because of resonance, here magnitude of positive charge decreases. No doubt in it. But the nucleophilicity of R minus is not sufficient. Nucleophilicity of R minus is not sufficient to attack on this carbonyl group. Carbonyl C double bond of carboxylate ion. That is experimental result. Nobody can guess that. Nobody can guess. So that's why you have to remember this. R minus cannot attack on carboxylate ion because carboxylate ion is resonance stabilized and the nucleophilicity of R minus is not sufficient to attack on this. But here you have to remember one more thing. If you compare alkyl lithium and RMgX, this is alkali metal. Alkyl lithium is more nucleophilic than Grignard's reagent. And its nucleophilicity is enough to attack on carboxylate ion. It can attack on carboxylate ion. Thereafter working is similar. It can attack. Okay. So particularly regarding RMgX, you have to remember. Now let's complete the reaction with alkyl lithium. See, RCOO minus is given with okay, let's start with carboxylic acid. This is a different case. Again R minus with acidic hydrogen. So first we get RCOO minus plus RH, of course here Li plus ion. Now that RCOO minus with again if present another mole of alkyl lithium. See, this can attack its, see what you get, RCO minus, here R, this is O minus. So this is the thing. Thereafter acidification, that is the later steps we can do the, so this is about alkyl lithium, right. Now let's see some conceptual questions, few questions. See, a compound has OH, COOH, COO, Cl, and say COO, CH3. Now, how many moles of Grignard's reagent is required? How many moles of Grignard's reagent is required to get this product? To get this product, here this is C, OH, here R, and here OH, here COOH, here COH, R. This is the question given. What is the value of X? See how to solve this problem. RMGX preferentially reacts with acidic groups. There are two acidic groups. So with first, let's write, see this is COOCH3 with OH. Okay, let's continue this. With these two, we need 2 moles of RMGX, R minus Mg, 2 moles of RMGX. There are 2 acidic hydrogens. That is the first one. So here we get COOCH3, and this is O minus, this is COO minus, this is COCl. Previously I told you with ester we need 2 moles of RMGX to get alcohol. See, let's write here. Let's take an ester, RCOOCH3 with the RMG, say R dash with RMGX. First step is loss of this. What do you get? R dash COR. Okay, this is the product. Again, it has keto group, so it can react with 1 more mole of R minus. So what do you get? O minus R, here R dash, here R. 1 more mole of Grignard's reagent. So in that way, totally one ester group consumes 2 moles of Grignard's reagent to form an alcohol. After acidification, it becomes as OH. Similarly, acid chloride also consumes 2 moles of Grignard's reagent. So totally 4 moles of Grignard's reagent. Now we get, see like this, we first we get COO minus, sorry, this is not a CO double bond O, R. Here also CR, O minus, and these are O minus, COO minus. After acidification, we get this product. Totally, how many moles? Here 2 moles, here 4 moles. So you have to look at the product also. So totally 6 moles of RMGX is consumed. So in that way, you have to look at the functional groups and you have to look at the product also. So based on that, you have to solve the problem, right? So this is about Grignard's reagent in brief, right? We have already seen Michael addition. Actually, not only for Grignard's reagent, the Michael addition can be written for any nucleophile, reaction of a nucleophile with a conjugated aldehyde or ketone. That is here RMGX, R minus. In general, a nucleophile. That is said to be Michael addition. Okay, we already done, right? In that way, we can do different problems related to Grignard's reagent. I have given different problems. We discussed different reactions of Grignard's reagent with different functional groups. Okay, on practicing, you can get the idea of solving different problems. Okay. Okay.